let's start. So it's a pleasure to introduce Francis Bonahon from University of California. So he's our Dean's speaker this week, and so we're giving a talk entitled Character Varieties of Surfaces and Kauffman Brackets. So you're welcome.
Okay, thank you. It's my first visit here, in spite of the fact that I've known some people here for a long, long time. So I'm going to talk about two things which apparently don't have anything to do with each other. So the first one is an SPA surface. Okay. So it's something which looks like this.
Orientable, or does it matter?
It doesn't matter. Well, it will be oriented eventually, but at this point it doesn't matter. And what really matters, connected perhaps. And you give yourself G a big group. And so what's important when you have a connected surface is that you have the fundamental group. So the fundamental group is a group, and I have another group here, so you can look at the homomorphisms from the fundamental group to the Lie group. And so you look at the group homomorphism, and you can consider all possible homomorphisms like this. Well, so it's fairly simple because you see, if the surface is compact, this is finitely generated, and if you want to give yourself a homomorphism from a finitely generated, finitely presented group to a Lie group, well, you need to specify the image of the generators. So you give yourself an element of G times G times G, but then whenever you have a relation here, you need to have a relation between the images of the generator. So what you see is that in this Lie group is defined by certain relations. And so this is an algebraic, if G is some kind of algebraic group, in practice, I'm always going to talk about SL2 actually, of what is the case so far. Right? I mean, the group of 2 by 2 matrices of determinant 1. So you see, what you're going to get is some polynomial relations between the coefficients of the generators, and so this is an algebraic geometric object. Okay, so we care about this, and then here you have an action of the group G by conjugation, and so you can take the quotient under this action. So if you're a naive topologist, you write it like this, but if you know a few more things, you realize that if you do it like this, if you take just the topological quotient, then you get a quotient which is not Hausdorff. So you have to stop being a naive topologist, so you have to be a smarter algebraic geometer. And what's smart about algebraic geometry is that the way you do it, you just put 2 bars like this. Okay, so there is a way to make it, just it's the standard quotient. And so that thing is called the character variety. Of the group here, of homomorphisms from this group here to that Lie group there. And let's call it R, G, and then normally of pi 1 or less, but I'm just going to put S here. Okay, and that's an object which comes up in a lot of branches of mathematics. So in algebraic geometry, for people who study, in string theory, that comes up as a space of flat connections on certain bundles over surfaces. Okay, so you have in gauge theory, this object comes up all the time. And then, if, like me, you spend a lot of time doing some hyperbolic geometry in low dimensions, when you do hyperbolic geometry in dimension 2, that's where the case where the Lie group G is PSL2 of R, Okay, you study those things. If you do hyperbolic geometry dimension 3, well, 3 means 3-dimensional manifolds. You often cut them along surfaces. That's where how the surfaces come up. And then you're going to apply this to the group of isometries of the hyperbolic 3 space. So there is quite a bit of mathematics based on that, on this character variety. And now I'm going to talk about something completely different, which is the Kauffman bracket. So it's a completely different area of mathematics where you consider, I want to leave a little bit of space here. So you consider knots and links. In R3 in the 3-dimensional space. So something like this. Okay, that's straightforward, and then to make it a link. So a link is a 1-dimensional submanifold of R3, and then if it has only one piece of string, one component, then it's called a knot. That's just that. And the problem of knot theory is to be able to tell when two knots are different, namely when you cannot move one piece of string to another one. And usually people use invariants, and a famous invariant is the Kauffman bracket. So I'm going to write it as a definition. The Kauffman bracket is a map. So first of all, I need to have a number given, a, and let's make it a complex number, not 0 given. And A underlines my definition. So the Kauffman bracket is a map where you take all possible links in R3, so in 3 space, and you go to C, so this map I'm going to call it curly K. And I need something here, I need framed links. So actually, I'm going to write it, but very small. That's why you're taking notes, it says frame. In other words, if you know what a framing for a knot or for a link is, it's fine. And it should be there all the time. And if you don't know, just forget about it. What a framing is the trivialization of the normal knot. It's a mouthful, and we can forget about it. And it has 3 properties. The first one, which is isotropy invariance. Says that if K is isotopic to K prime, then they have the same bracket. Okay, in other words, it's a knot invariant. And that's what these things are good for. Namely, if you're given 2 pieces of strings, and if you want to show that there is no way you can move this string to that one, well, you can put the Kauffman bracket. If by any chance you find different values, then sure enough, there is no way you can move one string to the other. It doesn't tell you that when they have the same value, you can necessarily move the string to the other. But that's what's useful about it. And what's special about the Kauffman bracket as opposed to other invariants, it's the skein relation, which says that if I have 3 knots, three links, like one which looks like this, one which looks like this, and one which looks like this, and if I consider them, so if I have 3 links which are the same everywhere except in a little box where they differ like this, the Kauffman, I didn't leave quite enough space, but okay. Let me move this one a bit on the side. There is a relationship between the Kauffman brackets, namely the numbers here, are associated with 3 links, which is that this one is A times this one plus A inverse times that one. Okay, now, don't ask me where this comes from. I will tell you a little later, but right now, well, why not? It's a linear relationship between these things. And then the third condition is the superposition rule, which is the following. If I have a first knot, and I put it on top of another one, so I'm not going to try to make something too fancy, but let's see. So that's K2. This is K1. And then these are knots, but when I put them together, I get a link. And I can consider K1, K2. Let me put a dot here. That just means it's the union of these two here. And I take the variant of that. And the formula is the one you might expect. Then it's the product. Okay.
So they're not tangled.
I'm sorry?
Red and blue are not tangled?
Tangled?
They're non-linked.
Yes, it's not, yes, they are not tangled in that sense. Yeah. It's one on top of the other, way on top. Yeah, that's why it's a superposition. It's very important that the red knot is way, way below the blue one. Okay? Okay.
The 3D board wasn't working fully there. It's
The what?
the three-dimensional board.
Yes. And so what we have is that we have a theorem due to Kauffman. So what exactly? I would say 85 on it, which says that there exists a unique Kauffman bracket. In other words, if you have a map like this, it's completely determined by these three properties, and what's really important that there is an invariant which satisfies these three properties. That's really what the hard work is.
So actually non-zero or something?
What?
Okay, well, zero is one.
If you do it right, no, because you're going to have problems here with zero or whatever. Yeah.
Just say K of the odd knot is 1.
Hmm?
K of the odd knot is 1.
Did I say, no, K the knot is minus a square minus, so with the,
What is A?
I'm sorry?
What is A?
A is a number function which we chose, and for instance, okay, so for instance, K of the knot, loop,
Basically, that's the reality condition.
is minus a square minus a to the power minus 2, and that comes from condition 1 and 2. For instance, you play with tricks. Very
kind of.
Yeah, there is a trick. Okay. So, let's just give you that example. Anyway, so, it exists, there is one, it's useful, and by the way, it's closely related to another invariant which is called the Jones polynomial. And actually, the Jones polynomial is part of a big branch of mathematics called quantum topology, because so what's behind the Jones polynomial is something deep, which is the quantum group UQRSL2, and then you can do things with more different quantum groups. So you can expand the topology. There is quite a bit of interesting mathematics here, but here I'm just focusing on knots. And so, knot theory, I told you that the problem is, given two pictures like this one, two pictures of strings in space, can you move one string to the other? But you can do that look, when I describe this, I use only a two-dimensional blackboard. Namely, I use two-dimensional pictures. And the idea of moving the strings, you can express that just in terms of pictures. So actually, it's a two-dimensional problem in the plane. So actually, I'm not doing things in R3. It's actually something to do in the plane. And the plane, well, that's an interesting surface, but after a while, it gets a little boring, right? Yeah? So we consider more general. So for instance, this picture here, look, this is in R3, but look, I can draw exactly the same picture on the surface. Yeah? Yeah? So let's look at this. So now I'm going to get a, so let S be a surface. I'm not specifying anything, but it has to be two-dimensional. Okay? And I'm not going to talk about the Kauffman bracket, but I'm going to talk about a Kauffman bracket. In the surface S. And then I'm going to consider framelings in what? So what do I mean here when I draw? So what do I do? I take a surface, and perhaps this time, my picture, I can go around the surface. Eh? So what I'm doing is I take a surface. Actually, oops, I forgot something really important. This is joint work. Oh, and it's videotaped in addition. And actually, she's had undergraduate students work on problems related to this, and they gave her that wonderful torus blackboard. What it is, it's an inner tube of wire, and it's painted with blackboard paint. And so you can draw pictures on it. So you have this torus, and you can draw pictures like this on the torus. Okay, so that's the picture. But if you want to do topology, so you have to encode this idea of crossings, and it's really important where the crossing is like this as opposed to that. And so the way is that what you do is you put a thickening of the surface, and in the thickening you say whether the string goes like this or like that. Namely, you consider links in the surface cross 0, 1. And then look at my conditions. Isotopy invariance, well, that makes sense. So isotopy, that means that there is a diffeomorphism of this thickened surface to itself, which is isotopic to the identity, namely which you can continuously deform to the identity, and which sends this guy to that guy. And what you require that when that's the case, then they have the same invariant. The scale relation is exactly the same. You describe it in a little piece. And the superposition rule, look, my surfaces tend to be yellow. Look, my superposition rule makes perfectly sense for knots on the surface like this. The main idea for the superposition rule is that you write, so that was your idea, that was your question about whether one is way below the other one. What you say is that you write S cross 0, 1 as S cross 0 to 1/2 union S cross 1/2 1, and you're going to put the knot K1 in here and the put knot K2 in here, and so then you get this knot K1 K2 in here, and that's just beginning like this. So that's how you define that's how you define these superposition. It's really important, however, that we have this surface cross 0, 1. If it was the first two conditions make sense for any framelings in any three-dimensional manifold, but here you need to be able to stack the three manifolds. So that's really important, and that's why it's a That's why that's why it's related to something which is two-dimensional more than three-dimensional. Okay, so you can always make a definition like this. We have something in R3 in the plane. Well, let's see if I can generalize on other surfaces. So, you know, mathematics does progress by generalization for the sake of generalization, but usually you don't get the best mathematics that way. And here it turns out that yes, it works very well because it has deep connections to the other problem over there. And so the connection, let's look at an example. Where A is equal to plus or minus 1. And so I said, I have this parameter A, which could be anything. And so let's take A equal to A minus 1. So there is a little bit of a lemma, which says that when A is equal to plus or minus 1, A inverse is equal to A. Are you following me so far? Okay. And
Can you prove that?
in the homework. What's important about A and A inverse is that these are the two coefficients here. And what's the difference between these two? These two elements, that one is obtained from the other one by rotating. And so if you think a little bit about it, the outcome, you get that that implies that K, the invariant of, if I have a crossing like this, is going to be the same as the other crossing. By applying this formula rotated by power 2, and because A is equal to A inverse. Well, this is telling you something. It's telling you that when you let the curve cross itself, you don't change anything. So actually you can forget about it. And so that tells you that the knot K of a knot depends only on the class of K in pi 1 of S. Okay? Well, you know, fundamental group, some of you have learned about the fundamental group not that long ago, but for people like me, it's not that news, right? So it's boring a little bit. Well, perhaps not. So here is a theorem, and I'm going to give credit after that. And here is a way to create, so the point is that for A equal plus or minus 1, it's a problem only based on the fundamental group, and I'm going to try to put this guy in the picture. And that's going to work for, this is A equal minus 1. And so part 1, part A, if R from pi 1 of S2, and now I go to the group SL2 of C, is a group homomorphism, that there exists a unique Kauffman only one in brackets. For so K R for A equal minus 1, such that is the following. So you need to associate a number to a knot in the thickened surface. So for every knot K in S cross 0, 1. And when I say knot, I mean connected with only one string. Okay? So what you can do is that you have this knot, it's a curve in here. So you can consider its class in the fundamental group. Then you can apply your group homomorphism, so you get a 2 by 2 matrix. And then you can take the trace. And then you can put a minus sign in front. So actually, there exists a unit here. And it turns out that this is a Kauffman bracket for a equal -1, namely it satisfies. So I explain it satisfies the scale relation. -1, so the scale relation is this final relation here. And the idea, the reason why you have that is in a relatively famous trace formula, which says that for every, if I take two matrices, capital N and capital N in SL2 of whatever, K, and field, if I take the trace of M times the trace of N, this is equal to the trace of Mn plus the trace of Mn inverse. Okay, so it's a standard formula in SL2. Actually, it's just a way to re-express the property of the fact that a matrix, when you evaluate the characteristic polynomial of the matrix, you get 0. That's Kelly Hamilton. So it's a well-known formula in SL2, and you see you have two matrices. When you have two curves, it says something about the product of the images of the two curves with the combination like this. Well, combination, that's something like this. Now you have to take into account there are many cases according to whether in this relation, when you start here, when you follow the string, do you come back here or there or there? So there are many cases. And the minus sign here is specially designed so that you get the same formula all the time. And also, that's why you get the same with the A minus 1. Anyway, it's a simple combinatorial fact, yes?
I'm not sure what you mean here in this theorem.
What I'm saying is that...
What does such that mean? Are you saying there's a unique bracket satisfying this formula?
Yeah, exactly.
So there may be other brackets that don't satisfy that formula.
That's why there is an A.
I see, okay.
Yeah, so that part, which is just the trace formula, is due to, so there are two groups, mostly I think Charlie Frohman, but Bullock, Frohman, and then a single person called Kania Bartoszynska. Oh, wait, now I have to, she's a very important topologist because she's the one handling NSF money to the topologist. And unfortunately, that means that I have to spell her name correctly. And I think there is an accent on the N, not on the U, but on the N, I think. And we could get S, yeah, I don't know. And then the other group is, well, another Polish guy, Shikoa. What's the date of Buffalo? How far is Buffalo from there?
A long way. 4 hours.
That's a long way? Okay.
4 hours, yeah.
Okay, so, and one of these, it's late. It's about 90, or pretty much 2000, minus epsilon. But there is another part, Firstly, every Kauffman with A is equal to -1 is obtained in this way. And that part is essentially an order result of Helling 1967. Okay, and the reason what Helling proved is that if you give yourself a function on the set of conjugacy class of a group which satisfy a property which satisfies the trace formula, and I told you that the trace formula is sort of equivalent to the scale relation for A equal -1. So Helling proved that if you have a map, if to each conjugacy class, if you have a map on I think in this case it's only a general group. It could be just a surface group. It's complicated because it puts something much more complicated in this paper. But essentially, once you have a set of maps which satisfy the trace relation, then it's the trace map, the trace function associated to a group homomorphism in SL2. And that works for large numbers of groups, fields, and so on. Okay. So, the upshot of this is that when A is equal to -1, if you look at the space of Kauffman, the set of Kauffman brackets for A equal to -1, it's in one-to-one correspondence with that thing with the space of group homomorphism. This is invariant. When you conjugate, you're not changing the trace map. And so actually it goes to the quotient like this, and so it's in one-to-one correspondence with this character variety here consisting of group homomorphisms from the fundamental group of the surface to my group here, which in this case is SL2. Okay? And then we have a very similar result for A equal -1, A equal +1, where take the corresponding brackets for A equal +1, well, it's in one-to-one correspondence with the point in a slightly different character variety where we take PSL2 of C. P means that you're taking the quotient by the center. In this case, the center is plus or minus the identity. But you also put the word spin here. And, well, so it's a definition which is a little technical. But the main point is that it involves group homomorphisms valued in this group here with some spin information telling you how to live them. What this is a twisted version of the other character one. And it's a cousin. It's a little bit, things are a little twisted by spin swap. If you don't know what the word spin means, don't worry. It's one of those topological. This is telling you, however, that there is some there is a little bit of algebraic topology underlying that, and it has to do with how you lift things from PSL2 to SL2. Okay, so the upshot of this is that when A is equal to plus or minus 1, this is well understood because it's these character varieties here. And I mean, well, it's not that they are well understood, but at least it's a very concrete object, and we have a bridge now between the case, the Kauffman bracket, my strange generalization of the Kauffman bracket, and these character varieties, which are important. Okay, but that was for A equal plus 1 or minus 1. And so, how about for a general A now? Because you remember, my upshot here is that when A is equal to plus minus 1, it's boring because it does not detect the linking. Yeah? So you start thinking a little bit. And so, what's boring here? So I'm not proving anything. What's boring here is that it doesn't detect over and under crossings. Means in particular that whether you put your link K1 below and K2 on top, or whether you do it the other way, you're going to get the same thing because whereas what you see here in this case, this multiplication here is non-commutative. It's really, this is in general, this is not the same as K2 dot K1. It does depend on which one you put on top. Look, try to see. Sure enough, in this case, however, I can move one to the other, but if I put one more pole, there is no obvious way of moving the red string on top of the blue string. Yeah? So in general, this multiplication like this is non-commutative. And on the other hand, C is commutative, so these two should be the same. So it doesn't look like it's going to be very exciting. Actually, if you work harder, you find that there is no Kauffman brackets like this. So you remember I keep changing my definition. This is really the wrong definition. If you try with C, that cannot work. So what do I need for this condition to make sense? Well, okay, here, for one to make sense, here I only need to put a set. Okay, this is fine.
I lost you about a minute and a half ago. So suddenly we're changing. Could you say again why C is a bad choice?
Because it's commutative.
Because C itself is commutative.
Yes.
Oh, I see. Okay.
Yeah. And the process here looks non-commutative. And so, I mean, I'm not stating any theorem here. It's just meta-mathematics. Okay. So here, on the other hand, for the scale relation to make sense, you'll be able to make sense of this. Namely, you need to be able to take linear combinations. Namely, you need a vector space. And to make sense of this property, you need to be able to multiply elements. Okay, so a vector space where you can have multiplication, that's called I'm looking at the grammar students over there. An algebra, yes. So I can put any algebra. Well, unfortunately, algebras, there are lots of them. So what kind of algebra, what kind of non-commutative algebra do you know? So R and C, that doesn't count. Matrices, great. So you take the n by n matrices, and instead of writing matrices, you know, you have to take a basis in something. So I'm going to write this instead as the endomorphism of V, where V is a vector space. Of course, it's the same thing as matrices. It just looks nicer. I mean, it looks bigger. And it's a vector space, and in my mind, I could do it for infinite dimensional, but I'm going to restrict it to finite dimension. That's because.
And what A is? What A will be?
Let's give it a number. Actually, what's going to come is that
You want the central element.
this is driven by physics, of course. So you do that, and there is a philosophy which really was pioneered by Turayev, and then I'm not saying it. I think 86, he has a paper in 86, 87, something like that. And then it was further developed. I mean, really they wrote it better. I think Turayev had the idea, but really the details were developed by, so again, by the same, listen to the B, F, Burlock, Froman, Kania, Bartoszewska, and Precious Tishikova. Same two groups here, which is that a Kauffman bracket, and that's not the way they do it. They talk about the Kauffman, they introduce something called the Kauffman algebra, and here that would be what's called a representation of the Kauffman algebra, but it's the same, is that a Kauffman bracket for A, and so that's where I'm coming. A is a number, but let's write it exponential of pi I h with a finite h like this. Yeah? So the physicists think of this as this is supposed to be the Planck constant. And what?
It became a variable now?
It becomes a not yet. Well, it's a parameter. So yeah, anyway, yeah. I mean, you know, the physicists take the Planck constant and they look at the limit when the Planck constant goes to 0 and when it goes to infinity. You know, Witten has, I mean, there is this very famous paper of Witten interpreting, reproving the Morse inequalities based on this idea, where you let the Planck constant go to 0 and then you deform it to plus infinity and you show that things don't change, and so you give different interpretations according to where you are. So there is great work where you let you vary the Planck constant. Okay? So the Kauffman work for A is the same as a quantization of, well, what's happening, you see that when the Planck constant is actually 0, you get plus 1. Well, we can probably get the difference between plus 1 and minus 1. So of these two character varieties. The twisted version for A equal plus 1 is actually due to Helen Wong and myself. But I mean, it's only epsilon or epsilon to the power 10. I already spoke to go from here to there. So what's a quantization? You have a so I'm going to stick with words, and again, this is really meta mathematics. What's the quantization is that you have a space and you look at the algebra of functions in that space. Well, the algebra of functions is a commutative algebra, and then you deform it using a parameter h to a non-commutative algebra, so that when you do the lack of commutativity, then you look at the term of order 1 with respect to h. Yeah? So first of all, the deformation means that to every function you associate something in the non-commutative algebra, and actually this non-commutative algebra comes up in physics as an automorphism of a Hilbert space, namely a group of automorphisms of an infinite dimensional vector space, but you know, mathematicians cannot tell the difference between something infinite dimensional and something finite dimensional. Yeah, so that's my version. That's the topological version of the Hilbert space. Right? Okay, so you replace every function on the manifold by automorphisms of a vector space like this, and then in addition, if you do a power series expansion, the first term in H has to be a Poisson structure. And it turns out that on these things, with respect to, on these things, because you have a surface, there is a famous Poisson structure, which has many names, like Veil, Peterson. Then probably you want to put Atiyah, Bott, then Big Goldman. Poisson structure. So it's a classical Poisson structure on this character varieties, which is very important. And the scale relation here in this context actually corresponds to an expression of, so I didn't express what that had to do with knots, but bear with that. I will just say that the scale relation has something to do with the expression of this Poisson formula. And the way you go from knots to functions on that space is that when you have a curve, like in this case actually, you see, when you have a curve, you get this trace function where you see it as a function of R. So you can see that given K, you can see this as a function of a character variety, and they generate the algebra of all functions on the character variety. By the way, how long do I it's a 50 minutes or 60? 60, okay. Okay, so then it becomes even deeper. And what I want to talk about, so I have more than 10 minutes, is I want to talk about a goal, which actually I'm going to call the optimistic goal. So that's general A. It's not an example anymore. So the optimistic goal is classified all Kauffman brackets. For a given A. Okay, so for instance, for A equal plus or minus 1, this theorem here tells you how to find them, how many there are. Right? And for a general A, well, if A is not a root of unity, it's also relatively easy, because you look a little bit and you play with the scale relation and you find that essentially there is no way you're going to get a finite dimensional vector space. So actually you need A to be a root of unity. So I'm going to restrict attention. Actually what counts is A squared. And previously there was the case where A squared is equal to 1. So now we just want to prove a unity. And so being a root of unity, that means that A to the power 2n is equal to 1. Okay, so this is a natural restriction. What's not natural is that we need n to be odd. And of course we want a primitive root. I mean, you don't want A to the power 2n to be 1 for smaller n. So now we have this number which depends on A. And so we would like to find all of them, all of the Kauffman brackets. And how do you classify objects? Well, you want to find invariants. And so we're going to construct invariants, and they're going to involve the Chebyshev polynomials. Tn, let's write here in the name, of the first type. Oh, that's another guy. So what's the Chebyshev polynomial? Well, you know, when you teach calculus, you know that your students don't, but you do know that there is a formula for cosine n theta, and that you can express it as a function of cosine theta. And it's a polynomial function, right? So that's what the polynomial is, except that I want the normalized Chebyshev, so I can put a 2 here and a 1/2 here. But it's the same. So it's a little unclear why this trigonometric formula would have anything to do with either the character varieties which I have there, or the Kauffman brackets over there. So I mean, here is a hint There is another way, there is an equivalent formulation of the Chebyshev polynomial, which is the following. If I take a matrix M in SL2 of over whatever field, actually ring. If I take M to the power n, and I take the trace of that, well, and I want to express this as in terms of the trace of n, well, that's exactly the Chebyshev. That's exactly where the Chebyshev polynomial comes in. You get the second formula from this one by applying it to the rotation matrix of the angle theta. That's how you get that. Okay. So there is nobody doing quantum algebra here, right? Because the people who do the representation theory of SL2, they are more familiar with the other Chebyshev polynomial called Sn. And even the quantum topologists, because of that, are very familiar with Sn, which is the Chebyshev polynomial of the second type. For instance, in this context, it's related, you have a similar formula with sine instead of cosine, and Sn comes up there. And but to some extent, so the other Chebyshev is extremely common in the quantum topology. This one is quite surprising, except, so I only know two appearances of this in topology. So one is the paper of Froman and Jelka, and the other one is the Ukrainian school of quantum groups. That's why I know that the Ukrainians, the people doing quantum groups in Kiev, where they consider the case, essentially what those people did in Ukraine, they are doing in Ukraine, is they consider the case where the surface is the puncture torus. And they sort of completely solved this problem for the one puncture torus. Okay. So, what's the result? Well, the result is the following. I'm going to try again, starting with a Kauffman bracket. I'm going to create elements of the character variety, and it's going to use these Chebyshev polynomials. So now, this is the general formula for the Chebyshev polynomial. You have one for every number, and I'm going to use the one corresponding to this n here, which corresponds to the fact that I'm assuming that a squared, a is a root of unity. Okay, so here's the plan. So it's is the following. Let K from the space of findings in S cross 0, 1 to C. No, not towards. I graduate to the endomorphisms of B. B, and so B, a Kauffman bracket. I'm going to put more attributes for A. With actually, so if A to the power of 2n is equal to 1, I have two cases. A to the power n can be plus 1 or minus 1. I'm going to get two slightly different results. So A to n equal to 1 implies that an is equal to plus or minus 1. That one also I won't prove it. But I'm going to have the two cases. So if an is equal to 1 and n has to be odd, unfortunately, because otherwise the math doesn't work. And I want it to be irreducible. So what does irreducible? It's like in the sense of representation theory. It means that you go, actually, here, you go into the endomorphism of vector space V. You don't want that there is a subspace which is invariant, because then you could restrict to that. And so you want the dimension to be as small as possible if you want. And actually, every Kauffman bracket, you can decompose it as a direct sum of irreducible Kauffman brackets. So actually, you're not using very much. So then, so I'm going to leave space here, but here is the game. You take K, B, and naught, a frame naught, in the surface cross 0, 1, and to have a nice statement, I'm going to take one which has no crossings. Do I still have a picture? So here I have these blue crossings. I don't want that, I want just a knot. It can be very complicated. The picture can be very complicated, but it never crosses itself. Okay, so if I take a knot like this, I can take the Kauffman bracket. And then I can take its Kauffman bracket. And that's an endomorphism of V. Okay, that's a matrix. And usually the dimension is very big. Yeah? So it's a very big matrix. Okay, you have a very big matrix, and I told you that we're going to use the Chebyshev polynomial. So when you have matrices, you can evaluate the polynomial over them. And okay, you have a big matrix, and so it's really fun to do on the computer actually, because you take an example, you compute, you get this huge matrix, you evaluate so where the entries already are very complicated, and then you evaluate a polynomial of degree n over that. So what do you get? You get a huge matrix. The entries take several lines to each entry, several lines. But I haven't used the fact that an is equal to 1. So on the computer, on Mathematica, you plug in n equal 1, and then everything disappears. And you find the identity. Not quite. You find the identity of V times a number here. Namely, outside of the diagonal is 0. On the diagonal, you have all the same terms. And what these terms are, then, there exists a unique R in my character variety. Namely, R is a map from pi1 of S to S of the surface, to Sn2 to the space of 2 by 2 matrices of determinant 1, such that, you know that Kauffman bracket we had before, minus trace. I'm wrong here, it's the case for n is equal to minus 1, I'm sorry. Minus trace of R of K. Okay, that's the term you have here. But really, what's really surprising is the fact that you have this huge matrix, you plug in A to B, the precise root of unity, everything disappears, you get a diagonal matrix where all the entries are diagonal, and in addition, they correspond to this. What that means is that the coefficient here satisfies the scale relation with A equal minus 1. Okay, so what did I do? Starting from the Kauffman bracket with an equal minus 1, I get a point in, I get an element of the character variety. Well, if you think about the quantization nonsense, starting from a quantum object, which is a very complicated object, with a non-commutative algebra of functions, I associate to it a point in the classical object which is being quantized. Okay, physics works like that in general. It's like, so I call that the classical shadow. You have the quantum world, which is very complicated, and it has a classical shadow, which is a standard object. And then you have a similar result like here for A equal plus 1. So I'm not going to write it, it's a similar result. When an is equal to plus 1, and it's exactly the same statement, except that R now is going to be an element of this twisted character variety involving spin structures. Okay, the mathematics are the same, it's just the details are a little more complicated.
Do you need in on?
I'm sorry?
Do you need in on?
In what?
In on? Or even?
Oh, yes. Unfortunately. Actually, so you could do it when n is not odd, but then the machinery becomes very complicated. And actually, for me, I come here, these Kauffman brackets and so on, it's something I've known about because I went to a lot of talks. I mean, like other people in this room have been to talks about those things for a long time, and it was never my thing, really. I've been moving there, and in particular, I don't know very well the literature, and I discovered the literature, we find these kind of things occur before that in different contexts. For instance, there is a, let me finish. Yes, so you get this, and so in both cases we say that definition R is the classical shadow of the Kauffman bracket. Well, so if you look at the literature, where that really comes, there is a lot of literature on the Witten Rechetti, Rechetti topological quantum field theory. And in particular, that gives you a Kauffman bracket corresponding to roots of unity like this. And the people who studied those things, if you try to do it when n is not odd, you can do it here. So whatever they do here works so much better when n is odd. When n is not odd, the machinery becomes extremely complicated. And I think that in our case, we could also make it much more complicated, but we prefer to stay away from it. And so, for instance, if you take these Witten figuratives, that does give you a Kauffman bracket. With classical shadow. But it's boring. It's the trivial homomorphism. And and what we have is a converse, and then we need to stop here. So this is a very famous example here, where with a lot of mathematics built on that, and we have like a converse statement. Because conversely, the whole Witten Rechetti into relief not only gives you a Kauffman bracket, but it's built from it. Once you know the Kauffman bracket, you can reconstruct the whole theory, which gives you invariant of three-dimensional equals. And there is, this all comes from the representation theory of the quantum group UQ of SN2. And so we have this converse statement. So again, you see that conversely, given R in the appropriate character varieties, so either SL2 or C, or the other one, the 2 there exists a Kauffman bracket. With A2n equals 1, such that with the classical shadow in the symbol, Okay, it's almost a theorem. You need S with at least one function. Actually, I think 2 years ago, it was a theorem without this condition. And then, so you know, it's a series of 3 long papers. The first 2 are ready and deal with the case with functions. And then the last one was removing that one got a few problems. Essentially, I don't blame Helen. Helen blamed me. I made a mistake in the computation of dimension. I think it's going to come back. I think it eventually is going to converge, but we're not there. But certainly in the case with at least one function, you have this converse statement. So actually what we have here is a much more interesting deformation of the Witten-Reshetikhin-Torayev Kauffman bracket. And I think it's also going to lead to TQFT involving 3-dimensional manifolds with the homomorphisms from the fundamental group to SL2. I mean, that's, there is a motivation here, which actually dragged me into that thing. That's this thing called the volume conjecture. The volume conjecture is a conjecture which connects invariants of nonce leaks in S3 of this type, I mean, related to representations of UQ of SL2, to the hyperbolic volume of their complement. So something which lives in hyperbolic geometry and in SL2. So there is a conjecture there, which has been exciting people because it connects 2 things which are completely different, and you don't completely see the path. And that's a little bit what dragged me into that problem. I've become more to the hyperbolic world, but I've been learning much more about the quantum world. And it's beginning to smell good here. We haven't, clearly, we haven't made much progress towards the volume conjecture itself, but certainly, I think it gives very interesting mathematics, if I can say so. And it's, I find myself, I'm watching my words when I say it, when I know you're taping this. Okay, thank you.
Any questions? Yep. What does Kauffman think of this?
You know what? I haven't talked to him. Good point. I should talk to him at some point.
He's an odd guy.
Yeah, he's not guy. He's so Kauffman is the expert of manipulating pictures like this.
Yeah.
Yeah, and of realizing that it has deeper connections. So I think he would like that. What I didn't say is that the proof of this, actually, it's a kind of mathematics I've never done before. It's combinatorics. But, you know, essentially, and brute force combinatorics. You know, for an old guy like me, I'm sort of proud of myself. Usually it's a young people game. And originally we observed that on the computer. And actually, I have a funny story about the fact that we didn't know that there were 2 different Chebyshev polynomials. And we were using different ones. And then I was doing these simulations with Mathematica, and it wasn't working. Except, fortunately, for our Christmas vacation, we went to Puerto Rico on the beach, and I bought the computer, and I didn't have access to a library or something. And so I used the wrong Chebyshev polynomial, and the one we were not thinking of using. We were thinking of using the other one, because the other one you expect in quantum topology. And so I did that, and then I saw exactly what I described, where you have these huge matrices, and all the terms disappear. So we expected the result, and once you know the result is true, you follow your nose for the combinatorics. We have a very non-conceptual proof. It's very unsatisfactory. I'm currently working on putting it in a more conceptual context with one with a postdoc at USC. But right now, it's brute force, and it's fun, actually. So, I don't know if you know the quantum binomial formula, which is the kind of things Kauffman really likes.
No, I just wanted to ask about you have this,
You start with your Kauffman bracket and you end with an element of the representation variety.
Yeah.
And the element of the representation variety could be interpreted as an action by isometries of fundamentally the surface on hyperbolic free space, right? It's a homomorphism into SL2C. Does geometry, is that somehow hiding here? Is that of interest? The fact that you have this action?
That volume conjecture I alluded at says the mystery there is how could this Kauffman type of mathematics, combinatorial how could that select a very specific representation of the knot complement to we're back to Bob Miley, yeah. That was a logic. How can it select that very specific representation of the knot complement to the isometry group of H3? And so that's very unexpected. And that's why people are working on that. And so, to some extent, that's my hope is that this is going to explain why the machinery would select that. I mean, right now, the volume conjecture is only verified experimentally. I mean, it's proved that for figure 8 knot. And conceptually, it's not understood at all, unless your name is written, in which case you have a big picture, which is really nice, actually. Written is doing really interesting things nowadays, again. But for the rest of us, it's very unclear. But that's the interest, at least. Why would you get anything discrete for instance?
What would happen if you use the quaternions, say?
Here?
Yeah.
Well, so there are quaternions for matrices. Yes, so the quaternions that correspond to capital N equal 8, I think. So, no, 4.
4.
4. See, you remember,
Right.
it's because of A. So you're going to get the quaternions for n, the very low power of 2. Namely 4, 8, or something like that. So that will come up. That can come up.
And it just seemed like kind of a simplest, non-commutative
It's
next step up from
so,
complex numbers or something.
So Helen works in an undergraduate institution, Carleton College, and she has all these students doing their master's thesis on this thing. And it's fun because you can have relatively deep mathematics, but also mathematics you can explain to an undergraduate if it doesn't come that much. They play with
So let's thank our speaker again.